You can just watch the video, but yeah. So this is a cylinder, an infinity wire on the z-axis, of course. So we're going to use theorem the Gauss. Theorem the Gauss is the same thing. So it says flux. So the general definition of flux is the double integrate, then you say E as a vector, then dot ds as a vector as well, as simple as that. Then you equate to what theorem the Gauss says. Theorem says flux is given by q in over epsilon 0. The whole essence of using a cylinder which we call a Gauss surface is because here we're only going to consider the the charge that is enclosed. So let's say this cylinder has got a height of h. Okay, the height of this cylinder is h. Okay, so the only charge inside, we had an infinity wire. Okay, now the only length that is inside now is this wire of the length h. Okay, if you get this wire, if you get this wire, and that's the only charge you're going to consider. Okay, so this is how we go about the theorem de Gauss. So we're going to break down this integral because we know that the cylinder has got three surfaces, two circles and a surface lateral. Okay, this surface. Okay, so and then I told you that by convention they said that the direction of the upper surface is going upwards. Okay, the directions are important. So you put the directions like that. Then the direction of the down surface is going down. Okay, then the direction of the lateral surface is going this direction. Okay, that's how you go about a theorem de Gauss. These are going to help you. Then you can name this surface as S1. You can name this surface as S2. Then you can name this lateral surface as S3 if you want. Whatever you want, whatever works for you. Then here what we're going to do is this integral can be broken down because this is a surface integral. The double integral is a surface integral. You can break it down into three. Okay, so we're going to say E dot ds1 as a vector plus double integral E dot ds2 as a vector, then plus double integral E dot ds3 as a vector. Okay, so once you manage to do this, the reason why we break down this integral into three, because this is the only way you're going to evaluate this integral. This integral simplifies. Okay, now the other rules of integrating are, the dot product here. The dot product, the rule of dot product says the two vectors should be the same direction. Okay, now the question that the question that you need to ask yourself, the reason why we knew that we had to first of all find the direction of E, we said E is in the direction of the radius. Okay, so it is in the direction of the radius and the variable is R. Okay, so in short, the direction of the radius can be this direction, this direction, this direction. Okay, so in short, E will only conform to this direction. So if these two directions are not perpendicular, this integral becomes 0. Okay, the dot product of two vectors that are not perpendicular, that are not parallel, is 0. Now the surface ds1 and E, the S1 is this direction, then the E we've said it's only dependent on the radius, so it's in this direction. Okay, so this integral will be 0. This is the beauty of doing this. So this integral will be 0. Okay, even S2, as long as they're not they're not parallel, collinear, or whatever weight, so even this one will be 0. So the only from the three integrals that you've broken it down into, the only integral that will be valid is this one, and it's going to be valid because S3 is in this direction. This is the direction of E. Okay, so from these three, you only have this will only be equal to the double integral dot ds3. Okay, now my question is, so now you also check now this e always, whenever you're using theorem de Gauss, e always comes out of the integral, always. Okay, but I'm also going to give you the logic behind the integrals, why we take it outside. So the reason why we take it outside is because the radius on this surface is constant. So okay, don't worry about that. But e is only dependent on the radius. This is why knowing the variable. Okay, so knowing the direction helps us know which dot products will be 0. But knowing the variable helps us take this outside. Because on this surface, the radius is 0. Okay, the radius is constant, I mean, it's not 0. Okay, that is the distance from here to this surface is the same. So e, always this e goes out, but we just don't take it out for anything. So then see, once you want, if they are in the same direction, what the other way you can, the scalar product gives us the scalar. So this will now, we just multiply e ds3. You forget about you now forget about the vectors. That's how we do it. So you just multiply this, multiply by this. Okay, so this side, this has now been converted to a scalar. Then you can now take e outside the integral. So we are going to have ds3. Okay, then I told you guys that whenever you are integrating, whenever you don't have anything, you're integrating double integral, surface integral on a surface. The answer is that surface. Surface. So it's going to be E S3. As simple as that. Okay, to repeat, E and DS1 are not in the same direction. So this will be 0. E and DS2 is also not in the same direction. This will be 0. So our integral is just going to be equal to the double integral of E dot ds3. Okay, E and ds3 are in the same direction. So now here you can now convert it into a scalar. You're going to have double integral E ds3. Okay, then the E is only dependent on the radius, so the E can go outside. Always the E goes outside. So we're going to have ds3. Okay, so this, then the integral on a surface is always that surface E S3. Okay, now the question is, what is S3? Okay, S3 is the surface tetrad. So we have a cylinder, we have this surface, and we have, if you remember how to use the total surface area, we used to do this a lot in basic math. So this length was 2 pi r, just to remind you. Okay, I'm not going to go into this. Then the height here is h. Okay, so the surface S3, we can calculate it, isn't it? I'm sure you remember. So S3 will be equal to 2 pi r h. Okay. So so E S3 will be 2 pi r h, if you remember. Okay. This is the surface S3, the retro surface. So we've now established the left hand side. Okay, the left hand side is equal to, which was a double integral, surface integral. This is now equal to E 2 pi r h. Okay, we can now work, the hardest part is the left hand side. The right hand side of the formula, which says flux, which is generally given by the double integral of E dot ds, is given by q in over epsilon 0. Now we've established that this side has given us 2 pi r h e. So is equals to, what is q in? Okay, now you come back, what amount of charge is enclosed inside? Okay, what amount of charge is enclosed inside? So the amount of charge is enclosed inside, this is just the portion which is enclosed inside. Sorry, I've gone overboard. So this is the amount of charge enclosed inside. So the length of the wire enclosed inside is h. Okay, then this is a continuous distribution of charges. So this charge will be equal to, okay, line density multiplied by the length. Now the length of this wire is what? H. Okay, so this is how you find the charge. Always when finding a continuous distribution of charge, if it's a wire, we're going to use lambda for line density. So H multiplied by lambda multiplied by H. So this is the amount of charge inside. lambda h. So where there's q in, you put lambda h, because the length h is the only length inside over epsilon 0. Okay, so now what we're trying to calculate is the electric field, show electrostatic. Okay, so the show electrostatic will now be equal to, you now make the show electrostatic a subject formula. So you find that this h and this h will cancel. Okay, so the show electrostatic will now be equal to yeah, lambda over 2 pi epsilon 0 r as the answer. Then this is in the direction of the radius. Of course, we established that the direction of this is in the direction of the radius. Or you can give me a magnitude. The magnitude is just without the unit vector, 2 pi epsilon 0 r. So this means that the show electrostatic is just dependent on the radius from the calculation. Okay, so if the radius if the radius is big, the e will be smaller. That is,
Tita.
yes. So that's how we find the e. So for the wire, and the answer is always the same as long as you have a wire. The only thing that would change is when maybe we orient a wire in a different way. Let's say we put the wire in this way. At first, the orientation of the wire, most of the times we use this orientation, but if you put the wire this way, you're going to put a Gauss surface like this. Then you're going to see which surfaces will be equal, but the magnitude will always be the same.